have an organizational committee chair presenting, James Freerichs, for those who haven't had the pleasure to meet him yet. James will take over.
All right, thank you very much. I made a promise to my Ukrainian colleagues that I would, as long as the war is going on, I'm going to start every one of my talks with a moment of silence. So let's just have a brief moment of silence for solidarity with the citizens of Ukraine. Okay, thank you very much. Asher Perez is a very interesting quantum physicist. I love a lot of the things that he says. He wrote a very interesting textbook. And the quote that I really love that he says is, quantum phenomena do not occur in Hilbert space, they occur in a laboratory. And this is something that we should not forget, especially when we're teaching physics. That we are physicists, we should be teaching physics, not math, in our physics classes. And quantum mechanics is one where we often err much too much on the other side, where we're teaching much more math than physics. I also want to point out that there's an interest in trying to relate recent research with things that you're going to present in the classroom. And what I'm going to show you today, I think, is a really wonderful example, and I believe this can even be given at the high school level. It's not something that requires a deep knowledge of physics, but the results that come out of it are really remarkable. Now, many of you might have said in the class that you cannot measure position and momentum at the same time. I know I used to say this. And then I never went to the next question, which is, okay, how do you measure momentum? I mean, after all, isn't your detector located somewhere? Or isn't your detector, at the very least, measuring the position of something at the same time? Well, it turns out that the most common way of measuring momentum is to measure position, and it's done with an experiment called time of flight. So the way that this works is you start with something that starts an event, that you start a clock when that event occurs. The experiment I'm going to describe to you, we're going to have an atom that is sitting inside a trap. The trap will be released, and the atom will move off once the trap is released. We know exactly when the trap is released, so we know exactly when to start the clock. Then the particle travels through free space. So it travels as a free particle until it is detected in the detector. You simply divide the distance traveled, because it's moving as a free particle, by the time that it took to get there to compute the speed. And then from the speed, you can, of course, get the momentum. So this is more of a philosophical question. At the moment of measurement, do I actually know both the momentum and position of the particle at the same time? I would argue that you are measuring the position, but yes, you do know the position and momentum at the same time. Is that violating anything in quantum mechanics? No, it is not violating anything in quantum mechanics. And I'll explain why in the next slide. So it is simply not true that you cannot measure position and momentum at the same time. And so I would encourage you, if you're teaching quantum mechanics at any level, that is not something you should be telling your students. What is true is that we cannot prepare a quantum state with definite position and momentum. But we can measure position and infer momentum as accurately as you want. So if you think about time of flight, if I make the time of flight really long, so the initial position uncertainty is the size of the trap. That's typically on the order of a half a micron or something. If I made my position measurement a mile away, now that might be difficult in a real lab, but I could really make it very long, then my momentum measurement is exceedingly accurate. It has an uncertainty of about a micron over a distance of a mile or something. I'm going to get a very accurate measurement. We can measure time incredibly accurately. We can measure position incredibly accurately. You could even imagine having your thing impale upon some target, some surface, and then get out a STM and measure it to atomic precision. We can get the momentum essentially as accurately as we want. That's for a single shot. So where does uncertainty come in? If I repeat the measurement, I get a different answer. And I get a different answer because the initial quantum state does have a distribution of momentum. It is not just one momentum state. But in each shot of the measurement, you don't violate uncertainty. Uncertainty comes in when you look at the relationship between many different measurements. That's a subtle point that's really important to keep in mind.
Delta P. Delta
That's
P,
right.
delta
It's the
X is
fluctuations.
greater
You
than
can't get fluctuations from one measurement. That's true. Nevertheless, most people will say you can't measure both at the same time. So time of flight gives us a great opportunity to both talk about real experiments, to talk about the relationship between collapse and what is actually measured, and to really talk about the subtle distinctions of the uncertainty principle and how it actually works. So where does the modern 21st century second quantum revolution come in? It comes in from the experiments from Cindy Regal's group. She shows us how to actually directly measure harmonic oscillator wave functions. It's an ingenious experiment, and I want to just show you over the next couple of slides how this works. So it's, one of the things that we also don't tell people about very much in quantum mechanics when we're teaching quantum mechanics is how you actually make any of these states. So we might solve the harmonic oscillator problem, and then you're like, okay, how do I make an n equals 17 harmonic oscillator state? Well, it turns out that's an incredibly difficult thing to do. So it's not that hard to make the ground state. If I can take all of the excess energy out of the system, it goes to the ground state. So ground state, people who work in atomic physics are very good at making ground states because they know how to cool atoms. And by cooling the atoms down to the lowest energy, I have a very high probability that I'm in the ground state. Then what she does, which is incredibly clever, is she has not one trap, she has one trap where the atom is sitting in. And she has another trap that she can bring close to it. And she can adjust the level of the second trap relative to the first one. So she knows the curvature of both traps, so she knows exactly where the energy levels are in each trap. And if she matches the ground state level of the first trap with one of the excited levels of the second trap, she can transfer from the ground state to an excited state with very good fidelity.
Why can't you just pump in photons of the right energy?
Because it is not that simple in these kinds of traps with the atoms. This is not an electronic system. This is a neutral atom in a trap. There's no simple radiative transition to rise it up to the next level. However, there are things that some people do like that, but you typically don't get like 100% transfer. This method really, you get 100% transfer, so you can really look at these different states. Okay, so this is imaged for you here in these examples. So you start off in the ground state in this trap on the right, and then depending upon where you put that second trap, how high up or down you put it, you can transfer to the ground state. In fact, if you're going to just do the ground state, you probably wouldn't even do the transfer, but you can transfer to the first excited state or second excited state. And then they do time of flight. Okay? And again, each measurement just measures the momentum. What we know when we have free particles, the momentum distribution does not change after I release to a free particle. If you remember how you solve the free expansion of a Gaussian, the position expands, and in fact, that's what is needed to be due so I can actually image the atom in the first place. But the momentum distribution stays the same because it's a free particle. There's no forces acting on it. Momentum doesn't change. Momentum distribution is the same. By using time of flight, when I let it expand far enough, I directly measure the momentum distribution by measuring the position. Okay? And this is what you get. So on the top, you have the ground state. That is a nice Gaussian-like profile. You can't tell that it's Gaussian just by looking at the little pixels that are bright or dark. This is the first excited state with nicely two lobes showing the two peaks in the harmonic oscillator ground state. The next one, it's a little bit harder to see here. I think it's better to see a line cut through the data. But that's the second excited state, which has two depressions in it. So I think this is a beautiful experiment. I think you can explain time of flight even at the high school level. And you can introduce students to some of these really modern quantum ideas very early on. And I just would like to encourage people to think about doing that. I kept this talk short. This is what I think is a great example of a second quantum revolution experiment that can be understood even at the high school level. And that's really all that I have to say. If you have any questions or anything else, I'll be happy to talk about that. If you want to see other resources of things that I do, I have a couple of MOOCs on quantum mechanics. One is for non-scientists called Quantum Mechanics for Everyone, which teaches about conceptual ideas. One is a full undergraduate quantum mechanics course, but it doesn't teach it by the traditional differential equations and wave functions approach, and instead emphasizes operator ideas. I also have a mathematical physics course, and this quantum.georgetown.domains also covers some of the research that I've been doing in this area. And with that, I'll thank you. If there are any other questions, I'll be happy to answer them.
So I come from a chemistry background, and when I would talk, I only taught at the general level, so high school, and my students would always be like, how do you just shoot, I would show them like the wave particle duality video, and they'd be like, how do you just shoot one atom at a time? How would you answer that for like a high school appropriate level?
So, I mean, with a two-slit experiment, you might be thinking more about doing photons than atoms.
Right, or like in this, and you're like, there's an atom in the harmonic oscillator.
But one of the things so I can tell you how it's done here. They really do have just one atom, but with the photon, you do not want to say that they take a laser and they just make the light really dim, even if you say like only one photon every half a second is going through the device, because lasers are classical sources of light. They always have what's called photon bunching, and they never act like single photon sources. So you should never say, even though lots of textbooks say that, that is not the correct way. So after about 1980, we discovered single photon sources. The first one was something called a calcium cascade source. And the way that that works is you have to shine two lasers, because the transition is too high, to excite an electron from a ground state up to an excited state. The excited state is metastable, but it doesn't decay coming straight down because it was a two-photon excitation. So it goes through an intermediate state and then comes down. And it's about a nanosecond delay in that intermediate state. So what happens is when it comes down, the first one, you can detect that first photon. And then, within the next nanosecond, a second photon is coming out. And this is the standard way in which they would create a single photon source. Now we have a number of other kinds of single photon sources. Many of them are of that same form. They're called heralded sources, which means there's two photons that come out as the single photon source, often in different directions. And I can tell that I have this photon by measuring this one, and then I know that I have a single photon around. We're not yet at the stage that you can push a button and say, I want a single photon to come out. Okay, that's not available yet, but people are working at it, and they're getting pretty close.
I feel like that's how a high schooler perceives it. That was like, I can just push a button and then one
I think
photon
almost
comes out,
everyone who has
so-
never looked into this perceives it that way as well.
Right.
Not just high school students. I know I used to perceive it that way.
Right.
I used to say dim lasers because, of course,
Yeah.
I only have one photon every, second in the device. Has to be a single photon source, but that's wrong.
If it's not the source, what about a neutral density filter that reduces the intensity of the laser beam significantly?
Again, there's a significant difference between a classical source of light and a quantum source of light. And again, you tell that because the property of a single photon source of light is that the photon can be measured once and only once. So the way you determine this is you put your source on a beam splitter with two detectors, and you measure how often do I get coincidences in the two detectors versus how often do I get just one or the other. If it's a single photon source, I always get just one or the other with no coincidences. If it is not a single photon source like a laser, you will find that you get some fraction that are coincidence measurements, and that's telling you that it's not really a single photon source. And these are experiments that were done within the last 20 years. Alan Aspect, who the recent Nobel Prize winner, did many of these kinds of experiments.
He also always measured both, right? That was the whole point of his experiment. He measured both independently.
That's the EPR experiment,
Right.
yeah. So you can use these, some of these heralded sources. You don't have to use them in heralding mode.
Right, exactly.
You can use them in a
Still
mode where you
has-
actually have two single photon sources that are correlated together in an entangled state, and then do interesting stuff with that as well. Yes. Yep.
So I have a question, something that I think I'm not so sure. So when you do your time of flight measurement, is the width of your, like when you showed your dots on on the light sheet, right? Is the width of that distribution of positions related to the momentum spread?
Exactly. It's essentially the initial position, which is uncertain by where it's sitting in the trap, plus essentially the velocity that the particle traveled times time.
Yeah, because in the old days, the way they used to do these experiments, they didn't have a single atom there, but they'd have a mod, like they have a trap
So
of
you
some
also
sort.
can do it in a
And then they
situation
do-
where you have many. That's true.
They
Yeah.
drop all the atoms at the same time, and then
Sure.
from the width they get the momentum.
Sure. There's lots of experiments that work
This
that
is just
way.
like doing one at a time and
I
getting the
believe
same.
this one uses one at a time. Yeah. Yeah.
Yeah, she does have a single atom trap with this new membrane.
So
type.
that's really one of the big developments because it's fairly easy to trap individual ions. And that's been around since the 1990s. But I'm not familiar with too many people who can do single atom trap.
I think it's possible, it's been possible for a while in an optical lattice. However, there's a lot of other problems and they're not quite as cool.
Well, with the optical lattices, you're trapping many. You
But
might
not
have one per
necessarily.
well, but you're trapping many over your
Right, so
device.
you can trap one atom per well. However, I think, if I remember this correctly, in the Boulder experiment, she has a special kind of tweezer.
She has just two traps, and it's like one atom in one trap, and she moves it to the other trap.
And the
so forth.
trap is
So-
not a light trap. I mean, a trap is a special light trap. It's not, it's inside the
But
vacuum.
this is the kind of stuff we're doing with the second quantum revolution, and that's why this is the interesting stuff that we should be telling our students about. Yeah. Yeah, agreed.
Well, thank you so much, James. We have a 10-minute break, and we'll have another parallel session in this room, in that room. In this room will be Tatiana